So I want to talk in this video about the infinitesimal divergence at a point. So remember, here I'm discussing something about the divergence. First, let's remember what was the definition of the divergence. We defined the divergence as the derivative of f1 with respect to x, f2 with respect to y, and f3 with respect to z. What is big F? Big F was the three components. Okay, so remember this was our definition. Okay, so here imagine you have a smooth function. Oh, we always deal with smooth functions. You have a point. Let's say this is my point P. I want somehow to explain the meaning of the divergence in terms of surface integrals. So we did surface integrals. We did the divergence theorem as a relation between the surface integral and the triple integral. Now I want somehow to see this definition here, the divergence definition, coming from a surface integral, just to make the idea of surface better understood. So if you take a sphere centered at this point, okay, so this is a sphere. So S is a sphere, let's say of radius rho, some rho bigger than or equal to 0. So this point is P, that radius is rho. So we're saying that this is rho, okay? I want to compute, so just to show you the plan of the coming computations, I want to compute I want to compute 1 over the volume of T times the surface integral over this S f dot n dA, n being the outward normal vector. What is T? What is T? T is the solid inside S. So basically it is the ball, the region inside the sphere. The sphere is the outer surface. The ball is the full sphere, we call it a ball. So T is the solid. We know the formula for the volume. So the volume of T is 4 over 3 pi rho cube. We know this, okay? So I want to compute the 1 over the volume, as mentioned here, times the surface integral. Now the surface integral represents the flux over the sphere. So you are taking when you write this integral here, you are taking the flux over the sphere. Then you are dividing it by the volume of that ball. After that, I want to take the limit as rho goes to 0. So what happens when rho goes to 0? Imagine you have a sphere of radius rho, and rho is very, very, very small. That means the volume of T goes to 0, because the volume, this is the volume formula. So basically you are saying you're taking the limit as the volume going to 0. So we will see how this quantity here, this limit, how this quantity is related to this quantity, okay? So the surface integral, again, is the flux over the sphere, divided by the volume, take the limit, something is going to happen. So how do we do these computations? So we know that to compute the surface integral of f dot n dA, we need a parameterization. So what is my parameterization? We are dealing with a sphere, so the parameterization is going to be the spherical parameterization. But here, remember, the center is not 0, 0, 0. So we are used, let me write it here. So if the center is 0, 0, 0, these are the coordinates. X equals rho sine phi cosine theta, y is rho sine phi sine theta, z is rho cosine phi. This is if you have the ball or the sphere centered at the origin. But what happens if you have another center like ABC? So imagine if the center was ABC, what happens? What happens is we make a shift. So imagine you take, for example, you have this ball here centered at ABC. You carry it and make it centered at the origin, 0, 0, 0. So basically the A goes back to 0, the B goes to 0, the C goes to 0. So it's like saying if the center was not 0, 0, 0, if it was A, B, C, basically what we do is we say, okay, X minus A is this, Y minus B is this, and Z minus C is this. So what is X? So X is A plus rho sine phi cosine theta. What is Y? It's B plus rho sine phi sine theta. And what's Z? C plus rho cosine phi. Okay, so this is the parameterization of the sphere if the center is not 0, 0, 0. Okay, then we compute R sub theta cross R sub phi. Remember, we already did these computations. This will be exactly minus rho square times sine square phi cosine theta, sine square phi sine theta, sine phi cosine phi. And because we did these computations, and because of this minus, this will be the inward normal vector. So to make it the outward, so the outward n is going to be rho square times this, just without the negative. Okay. Now once we have the parameterization and the normal vector, we are ready to compute the surface integral. So now the surface integral f dot m dA, what is it? It is the double integral. This is how we compute the surface integral. You take f, I'm going to write it this way. It is f of the parameterization, right? Dot the normal vector d theta d phi. Of course the phi, because you are dealing with a sphere, the phi is from 0 to pi and the theta is from 0 to 2 pi. Okay, so this is what we have. Okay, now I want to compute this integral somehow. I want to compute this integral. So the surface integral is as we just wrote. This is equal to the integral like this. Now what is f? What is f? If you look at f, f has three coordinates, f1, f2, f3. So basically when you say, okay, I want to substitute the parameterization, when you look here and you say, I want to substitute the parameterization into my function, that means you will substitute the parameterization, r theta phi. You will substitute it in f1, in f2, and in f3. So basically you will have the first coordinate as f1 of the parameterization, f2 of the parameterization, f3 of the parameterization, right? This is multiplied with the, as a dot product with rho square, remember we have rho square, times sine square phi cosine theta, sine square phi sine theta. This was the normal vector, sine phi cosine phi. So all of this is multiplied with rho square, d theta, d phi. Okay? So this is rho square is a constant from 0 to pi, from 0 to 2 pi. And what is the integrand? It's just f1 of the parameterization times sine square phi cosine theta plus f2 of the parameterization sine square phi sine theta plus f3r times sine phi cosine phi. All of this d theta d phi. Okay? Okay. What's next? Remember, if we go back to the previous page, what we wanted to compute, this is what we wanted to compute. We want to compute the surface integral, yes, but divided by the volume of the sphere, then take the limit as rho goes to 0. So now, basically, I want to compute compute 1 over the volume times the surface integral. If you agree, this will be, what is the volume of the sphere? It's 4 over 3 pi rho cube, right? Times the surface integral, so times what? Times something, which is exactly this quantity. Which is exactly this quantity. So let's look at this quantity in details. So what I'm going to do is, what is the integral? If you look at this integral, I have 3 integrands. So this is the first one, plus. So if I take only the first quantity, okay? So I take f1 times sine square phi cosine theta and d theta d phi. The phi is from 0 to pi. The theta is from 0 to 2 pi. What is this exactly? So this is the integral from 0 to pi, from 0 to 2 pi. Now f1, this is f1 of, what is the parameterization? The parameterization, as we know it, it's a plus rho sine phi cosine theta, b plus rho sine phi sine theta, c plus rho cosine phi. This is my parameterization. Okay, so this is, sorry, f1. This is sorry, this is multiplied with sine square phi cosine theta d theta d phi. Okay? Okay. Now what about this? Can we simplify this in any way? This is the integral from 0 to pi, the integral from 0 to 2 pi of what? Of what? At this stage, I think we need to remember some stuff, maybe from calculus 3, from calculus 3. So I need to remind you of something called Taylor series. Remember, what was the Taylor series for functions of one variable? So if you have f of a plus something, plus h, for example, okay? If you have f of a plus h, how did you find the Taylor series? It was f of a plus h f prime of a plus h square over 2 factorial f double prime of, okay, now if you want to continue, so f double prime of a plus h cube over 3 factorial triple prime of a, and so on. We all know this formula from calculus 2, okay? Now, if I want to stop at a certain point, I can do it. Remember, the idea of the Taylor series is that you can use the values of the function at a and its derivative at a to compute the values of the function at a plus h. So by knowing h and f of a, not f of h, f prime of a, not f of prime of h, you can determine f of a plus h. Now, the Taylor series continues to infinity. You have infinitely many terms, but at any stage, you can stop like this. So you can say f of a plus h f prime of a plus h squared over 2 factorial, which is 2, f double prime. Now, if you want to stop at the second term, you can do it. And in this case, you don't say f prime of a, but you say this is f double prime of some quantity that depends on h. A certain quantity, we don't know it. And the way we understand this, if this is a and this is a plus h, this x plus x sub h is some quantity between a and a plus h. This is the remainder we know from the Taylor series. Okay, so this is in the case of one variable. So what matters is for me is you take f of a plus h f prime of a plus h squared over 2 times a certain quantity. That's it. It is just the second derivative, but what's important is it's multiplied with h squared. Remember this. Okay. Now, if we look at the 3 variable case, so I have a function of 3 variables. So I have a plus h1c, b plus h2, c plus h3. Okay, so now what is the point? The point is I know the values of the function at a point ABC in R3. From ABC, I want to determine the values of the function at another point, a plus h1, b plus h2, and so on. Okay, so I want to determine the value of this point using the values of the function at this point. This is the idea of the Taylor series for functions of multi-variables. Okay, so how do we know this quantity? This is equal to f of a, b, c. This is very similar to this term. F of a plus h, you take f of a. Now my point is not 1 coordinate, it's a 3 coordinate. Plus we differentiate f with respect to x at the point ABC, but we multiply it with h1, this thing. Then plus you differentiate f with respect to y at ABC, you multiply it with h2, this. Plus you multiply fz at a, b, c with h3. These 3 terms together, the 3 terms here together, they generalize this term here. So here, because you had only one variable, you just take a. This is like the basic quantity I know. Now I know a, b, c. This is the basic point that we know f at. So we take 3 derivatives with respect to x, because this is the first coordinate, with respect to y, with respect to z. Once this is done for the first coordinate, plus there is something very similar to this. There is something very similar. It's about the second derivative. But what happens, what matters in the end, it is a quadratic function in terms of these h's. So if to make it easier a little, okay, if we take this h to be the same, this will be plus h squared times something. I don't care what this thing is, okay? I really don't care what this quantity is, but it will be a certain quantity in terms of h square. Very similar to this. You can revise, so if you just Google Taylor series for functions of 3 variables, you will see the formula. Now, this is not our goal, but I just needed to remind you of this quantity. Okay, so now going back to this integral, I have f1 of these 3 coordinates. I want to use the Taylor series to approximate this. So how do we use the Taylor series? How do we use the Taylor series? We take the derivative of f1 with respect to x at a, b, c. Sorry, I jumped to the second term. We take f1 at a, b, c, plus we take the derivative f1, we differentiate it with respect to x at a, b, c, but we multiply it with what? With the difference between the x coordinate in the new point and the x coordinate of the original point, that's a. So we get rho sine phi cosine theta. Then plus the derivative f1 with respect to y at a, b, c. The same thing, you take the y coordinate, subtract the b, so you'll get rho sine phi sine theta plus the derivative with respect to z abc rho cosine phi. And after this you will get for sure a certain quantity multiplied with rho square. I don't care what this quantity is. Okay, there will be a certain quantity. All of this is multiplied with sine square phi cosine theta d theta d phi. Okay, so this is my integral. Again, for the last term where I added the stars, because I don't care what the exact quantity is. You will see why I don't care. In general, we care, but in this case, in this scenario, I don't care. You will see why. Okay, let's go to the previous page to see the full picture. So this is what we wanted to compute. We had rho square, remember, we had rho square multiplied with this integral. I want to do this integral, multiply it with rho square, then I want to divide it by the volume of the sphere. Don't forget this, okay? So the idea, we took the first term only and we did some computations here. We did these computations. So now let's go and take so now rho square times the integral from 0 to pi, from 0 to 2 pi, just to show you this thing, f1 of r times sine square phi cosine theta d phi. This is what we wanted to compute in the beginning. Now in this slide here, in this page, we did these computations. So this integral is all of this. So now I want to copy all of this to the next page, okay? Okay, so this becomes rho square times the integral what is this integrand? We found it to be f1 at a, b, c plus derivative x. If you allow me, originally we have ABC, but only to save some space, I don't want to write this, okay? But we know it, okay? We know it. So this is multiplied with, rho sine phi cosine theta plus the same thing, f1 with respect to y, it should be computed at ABC, but again, to save some space, I don't want to write the ABC, times rho sine phi sine theta plus f1 with respect to z rho cosine phi. All of this plus rho square times some quantity that I don't care what this quantity is exactly. This all is multiplied with sine square phi cosine theta d theta d phi. Okay? Let's divide this. So the first quantity, I'm taking the first quantity as the integral from 0 to pi, the integral from 0 to 2 pi. What is the first quantity? It's f1 abc. Remember, this is a big bracket multiplied with sine square phi cosine theta d theta d phi. So I'm expanding this bigger bracket. So now if you take this integral, what is it? Cosine theta, you are integrating theta from 0 to 2 pi. This will give you 0 for sure. So the first term, this thing, for sure, it will give you 0 when you multiply it, of course, with this. Okay, now we go to the second integral. What is the second integral? Let me take the integral from 0 to pi, the integral from 0 to 2 pi, df1 by dy. I'm taking it dy, rho sine phi sine theta. This is multiplied with sine square phi, so this becomes a cube, cosine theta d theta d phi. Again, what we did here is we took this quantity, and we multiplied it with this because it's a bracket and we should expand this bracket. Okay? Okay. Now, if we compute this quantity, what is it? Because of sine theta cosine theta, and the theta is between 0 and 2 pi, this integral for sure will be 0. And this 0 is not the reason for sine cube. The sine cube doesn't cancel in this case because the phi is between 0 and pi. But what makes this integral 0 is sine theta cosine theta. Okay? So we did this integral and it is 0. After that, let's take f1 with respect to z. So let's take the integral from 0 to pi, the integral from 0 to 2 pi, the derivative of f1 with respect to z, rho cosine phi. Again, this is multiplied with sine square cosine. Sine square phi cosine theta d phi. Again, we multiplied with this quantity. Fine. Similarly, because of cosine theta, and theta is between 0 and 2 pi, this integral will be 0. Nice. So if we go to the previous page, this integral here gives us 0. So what is left? What's left is only this quantity. Let's compute this quantity. So I want now to compute the integral from 0 to pi, from 0 to 2 pi, of what? The derivative with respect to x, times rho sine phi cosine theta, again multiplied, if you expand the bracket, it's multiplied with sine square phi cosine theta d phi. Now if you look at this, this will be 0 to pi, 0 to 2 pi. Of course this one is constant, the rho is constant. Sine cube phi cosine square theta d phi. And the nice thing now, this integral doesn't equal to 0. This is not equal to 0, yes. It doesn't cancel because cosine square, it's always positive. Sine cube phi, because the phi is from 0 to 2 pi, it is not 0. So in this case, we need to do this integral. At least we have the rho, that's a constant. We have the derivative with respect to x, that's a constant. And let's do the integral quickly using Mathematica. So if we integrate from 0 to pi sine phi cube, the nice thing, the integral, so if we do the integral, just do it, it's a matter of computations. If you do the integral sine cube phi d phi from 0 to pi, it will give you exactly 4 over 3. And if you do the integral from 0 to 2 pi for cosine square it will be pi. This one, if you integrate it from 0 to 2 pi, it will be pi. Okay, so this is the integral. Now let's have our summary for this integral. So this is 4 over 3. Remember, the derivative was at ABC. I'm writing it here. So this is our final answer for the first integral. So remember, we wanted to compute this integral. We did the parameterization. We substituted the function. This is what we got. Then we only took the first part. After doing the computations of the first part, we found this here, this final answer here, okay? This was our final answer. However, remember, we want to multiply this integral with rho square. Then we want, remember the rho square comes from the normal vector. This is where the rho square came from. Then we need to divide by the volume of the sphere. So if we do this, so 1 over the volume of the sphere times the surface integral f dot n dA. In doing this, it's 1 over 4 over 3 pi rho cube times the double integral, which is what we did, and we had here f1, we had f2, we had f3, all these computations. So now if we just take the first part, so what was the first part? It was 1 over 4 pi over 3 rho cube times rho square this is what we're doing, times rho square, and this integral in the end, after doing these computations, it was 4 over 3 pi rho df1 by dx at a, b, c. Not only this. In fact, if we go back to this integral, remember, what we took is, when we did our computations, the integral computations, we only did the integral for these quantities. We did not do this integral. Remember, here we had a quantity. We had rho square multiplied with a certain quantity. I said we don't care what this quantity exactly is. Why? Now I will show you why. Because if you take it, regardless of what this quantity is, okay, so you will say, let me change the bracket. So if you take plus rho square multiplied with that quantity, I don't care what the quantity is, even after integration, I really don't care. What happens is, this rho square cancel, so you will have one row down. Then this row will cancel with this row. This row will cancel with this row, but you will be left with one row. So when you take the limit as rho go to 0, this term will be 0 for sure. So now what happens is this. So let's write these computations to make it clear. I remember this was about the Taylor series. Okay. So if we take the limit as rho goes to 0 for 1 over 4 over 3 pi rho cube times rho square times 4 over 3 pi rho df1 by x at a, b, c plus inside the same bracket rho square times a certain quantity. This will be, as we said, this will be cancelled with this. This row will be cancelled with this row. So basically it will be 1 over 4 over 3 pi times 4 over 3 pi df1 by dx at a, b, c. Okay. Then plus 0. Why is it plus 0? Because when you cancel this row square with this row, you will be left with a row. So when you take the limit as rho goes to 0, you will get exactly 0. So this means this gets cancelled with this, and you will be left with df1 by dx at a, b, c. Okay? So please. What did we do? This is very important. The summary is very important. We had a sphere of radius rho. We computed the integral. The surface integral. Then we took the limit as rho goes to 0. Now this integral had three quantities. This integral, in order to compute this, we had f1 plus something with f2 plus something with f3. That is this quantity here. We have this f1, we have this f2, we have this f3. We computed f1 only. These computations are only for f1. After doing all the computations for f1, we are left with df1 by dx at a, b, c. If we do the same computations for f2, and this is taking too much time, so if you do the same computations for this, you will get the derivative of f2 with respect to y. If you do the same computations for this, you will find that the derivative with respect to z. So in the summary, so what is the summary? If S is a sphere of radius rho centered at the point P, A, B, C, then if you take the limit as rho goes to 0, 1 over the volume of the solid, surface integral f dot nda, this will be exactly the derivative f1 with respect to x, the derivative with respect to y, the derivative with respect to z, of course at the point B, at the point A, B, C. And remember, what is this quantity? This is exactly the divergence of f at the point P. So this is what we call, first of all, this is the big relation between the divergence and the surface integral. This is the meaning of the divergence, and this is the meaning of the surface integral. Remember, the surface integral is the flux. So what we're doing is, what we're saying is, you have a sphere, you have a vector field. If you compute the flux over this sphere, and you take the average flux, so you divide it by the volume of that sphere. If this sphere was very, very, very small, you will get exactly the divergence at that point. So this is why the divergence itself, it can be looked at as like the infinitesimal flux at the point. So we imagine it, the divergence at a point. So for example, you have a function, let's say x squared regardless, okay? If you find the divergence, it will be 2x plus 3y squared plus 1. So if you find the divergence of f at a certain point, let's say 1, 1, 1, it will be 6. What is the meaning of the 6? So now, what is the meaning of the divergence? The 6 means if you go to the point 1, 1, 1, you compute the flux of this vector field over this sphere, and you divide it by the volume. So you're taking the average flux over that sphere. It will be almost 6. So you are looking at the point 6, you are looking at the point 111 as a very, very small sphere, and you're saying the flux through that point is 6. It's not a flux through that point. We call it infinitesimal flux. This is the relation between the divergence, the average flux, and the surface integral.